Nice to see you. Welcome
Nice
to
to
our
see you
workshop.
too.
Thank you so much for joining.
Hello, everybody. Great. So should I just start right away? I guess we are a bit late, so I just try
Yes,
to catch up.
apologize.
Okay, wonderful. Well, first of all, thanks a lot for having me here, and great that you guys are doing a great workshop with many interesting talks, and so many people are joining, which is really cool. So hello to everybody, and I think I will just start by sharing my screen, and I hope everything works out fine. Let's see. Okay, so could you just compare that it works, confirm that it works?
Yes, it works fine.
Okay, wonderful. Okay, thanks, Diego. Yeah, so as I said already, thanks for having me here, and I'm glad to give a short overview of some of the work we've been doing in physical human-robot interaction, which obviously is just a very tiny part of what we're talking about today. Crowdbot being kind of a very complex scenario. I'm just focusing in my talk today on very specific details, I guess, in one-to-one dyadic interaction between humans and robots, and especially on the physical interaction. So not so much about complex interaction algorithms, learning, and all these aspects. So I will keep them out entirely today and really try to give you kind of a bird's eye view on the focus on the physical interaction layer, and what are just some recent results we have, and I hope that's interesting for you guys, and glad to answer some questions in the end. And well, I mean, jumping just right away, I guess some of you know the robots we've been developing over some years now. So I think what we have achieved so far in terms of like real world physical human robot interaction is, I guess, that just to give you one example, that robots collaborating with humans in real world production is nowadays reality. So when I started my PhD, this was still a very long-term vision. Many basic questions were not even answered yet. And I think which is great to see is that at least we have not entered the age of human-robot collaboration on the broad yet, but I think we all are happy that some real-world applications are actually taking place, and especially some of the very early visions of humans and robots closely working together in collaborative setups and not only doing automation, so more becoming assistants to humans. And many of the questions, I guess, that are relevant for this workshop have been risen back then already. So especially on the physical interaction side, I'm trying to shed some light on the safety, on the control, and on some low-level planning aspects that might be interesting. I guess we all know that there is more and more fields coming. We have the Crowdbots, which we talked about today, but I think what is also interesting is next to industry, we also see that some first works have been taking place, in also using robots nowadays in different application scenarios. So in kind of assistive setups, for example, in dentistry, there's been some recent work also of our group, really trying to see how can we use multimodal interaction patterns, not only physical, but also visual cues and naive ways of interacting with robots, also for non-experts. So I think we can see that this notion of physical human-robot interaction, also bridging towards more cognitive levels, is becoming more and more important, not only in the lab, but also in real-world applications that I guess many of you have been also contributing to a lot. I just wanted to make a point here so that we are not only talking about industry, but I think we are indeed more and more talking about service applications, professional service applications, also medical applications, where assistive systems with some level of autonomy and learning abilities become more and more important. And obviously, for this, one of the fundamental aspects that we need to ensure, especially on this closeness, not so much what Luca was talking about before on the navigation level, but more on the tactility, on the physical interaction level. The notion of tactile robots going back to the beginning of the 80s, when torque control, force control, and all the basics were kind of, to some extent, introduced. So have been a long-term vision in robotics, as we all know. And over many decades, many groups have done some really cool and important contributions, ranging from Osama's potential field, operational space control, Bruno's, since we are in Roman in Naples, I guess it's also due to really state that Bruno Siciliano has done very tremendous work in force control that has also inspired lots of the things we've been doing, inverse kinematics and so on. And also Gerd Hirzinger, who was my mentor many years ago. So I think we all know that these kind of basics were always a target, but not so many robots were there that could actually physically interact. So we've been putting lots of effort also back then in the collaboration when I was still at DLR, together with KUKA, to commercialize the KUKA lightweight robots and really bring robots to the real world that can physically interact, that have a sense of touch, softness in the control, but also kind of a tactility, meaning tactile control, more low-level autonomy that can very quickly respond to environmental and contact changes. And with this, have not only the ability to be guided and to be compliant, which we all know kind of emerged into what we call nowadays soft robotics, but really become tactile systems that can dexterously use their sense of touch in a way that also low-level learning abilities can be enabled. So I think this has been kind of an important step. However, with the physical interaction of humans and robots and the ability to actually make something out of the sense of touch that is more than mere compliance, I think it's even more important that safety analysis is a fundamental aspect. So we need to make sure that the famous law of Asimov, at least the first one, is somehow ensured. And I've seen that also, I think Norbert Elkmann is here, who has also done some work in safety and robotics. And we have been among the first ones together with Antonio Bicchi and Osama Khatib after, I guess, Yoji Yamada in Nagoya, beginning of or mid of the 90s, who has done some first work on injury and on pain perception in robotics. We try to understand fundamentally, so if we have a physical interaction between humans and robots, is this actually safe? How can we interact with this, and how can we quantify safety? And safety meaning true injury, so really more in the levels of, can we quantify the impact result or the causality between in a robot with its inertial velocity and surface geometry causing certain types of injury, and can we quantify that to some extent? Obviously, safety has two levels of abstraction. The first one being the locality, so essentially a robot in its local configuration queue, having some reflected impact dynamics, meaning the inertial the reflected inertia in the certain collision direction, the velocity, and the local curvature. But also there's the question of global design and planning questions. So can we actually quantify the overall kind of safety level of the design? Can we use this in designing robots? And can we actually use this on planning level? So I think these are the two main levels of abstraction. So in order to give you kind of a naive way of interpretation, obviously kind of this the big questions when you have built a robot, obviously you can only control. However, one of the fundamental questions we obviously have in designing robots is how can we design them safely, such that as little as much control intervention has to be done. In particular, obviously we want to not only design the surface geometries, but also actuation. And we all know the big movements in variable impedance, variable stiffness actuation, and others that led to various new designs over the last decade. One of the early works, yeah?
Are we seeing the first slide? Is that?
Oh,
we are stuck in the first slide.
Oh, sorry. Why? Oh, you didn't tell. Okay, you could have just told me.
Sorry, we were listening to you, and I just started noticing that. Yeah.
Ah.
We're missing some.
Let me just see whether I can. How does this work? Okay. Anyways, right. So the safety that we've been doing 15 years ago was essentially the first human-robot collaboration experiment in terms of crash testing and understanding how dangerous are robots that can actually interact with humans, and can we use standardized crash testing devices. We did some experiments with humans, obviously this me being much younger and much more stupid doing experiments like this. I guess some of you know these videos. So essentially this was the first basics of understanding, are these robots that have been designed for safety dangerous, or are they actually fundamentally safe if you have collision experiments, and then trying to understand what the fundamental injury that could occur in the worst case is, especially in this particular case you see here. So one thing that we've been doing over the last years was then to really put together all the safety data that has been there for many years of injury research in not only robotics, but especially in automobile crash testing, injury research in biomechanics, and so on and so forth. So we've been put together 70 years of research, more than 2,000 publications were screened, that finally made it into some of the works to try to understand, can we actually leverage all that knowledge that have been there in biomechanics research and put this together into one map that essentially lumps all together regarding impactor mass and impact velocity, and what's the injury that would occur by means of what we call quantifiable biomechanics-based injury rating. And what we see here is, for example, the injury coming from approximately 150 papers that were reviewed for the AIS scale in terms of chest injury by means of compression criterion or other biomechanical injury indicators. What is important is that you now basically see that the mass and the velocity, so the fundamental quantities that you have during an impact, can be separated obviously between safe and unsafe. So red being obviously a certain level of injury, blue being no injury according to medical observation. And this idea of essentially trying to understand impact velocity and impact mass and putting them into one fundamental framework, which we call the safety map or the mass velocity scale, is essentially putting the robot dynamics into one plot, being here the fundamental safety map representation we published 2 years ago, which basically puts together the robot velocity and the robot reflected mass into one dimension, and the other one can then be essentially the human body part that then runs through this understanding of human injury and can be plotted into the same plot. And obviously the intersection between these two areas is where this particular robot can in principle harm that particular body part. So this essentially brings together human injury understanding and robot dynamics into one representation that is fundamentally physically motivated without any fundamental assumptions or kind of all these weird calculations that we have seen over many years now, how to bring these two together. So this really unifies on very fundamental energetic properties, which then essentially gives us the chance to understand the global properties of a robot. So here are two examples: the lightweight robot 3 we did back then at DLR, and the Puma system, plotting the inertial properties and putting them together with the fracture forces of the frontal bone of the human forehead. And then what we see here, that for this particular surface that we are assuming in this case, no injury can be generated according to all existing biomechanical data for the entire range of motion, given in this particular example no additional payload for the robot. So this shows that you can now basically bring them together into the design level. So you can essentially plot the inertial properties of a robot over its entire workspace and then intersect this with biomechanical injury data. And this gives you a notion of how dangerous is fundamentally a robotic design in its inertial, velocity, and impact curvature properties. Okay, so now that we have some tools on making robots safer in motion and in design, which I unfortunately couldn't tell you on all the pictures, but I think roughly the idea became clear. And then obviously one very important aspect is the monitoring of collisions, which I guess also many of you have seen so far. So many years ago, we did these basic monitoring works, collision detection and reaction based on what we call Momenta Observer, together with Alessandro De Luca at dynamic impacts, but also at very sharp impacts. And the idea was essentially that we put together not only the inertia of solving the dynamics equation algebraically, but we put together a so-called momentum observer that, because we don't have acceleration typically available in robots, estimates the external torques that come from the external collisions via this momentum observer, and then giving us a pretty accurate estimation of the external torques in the generalized space in order to then do all the monitoring estimation and so on that you have seen so far. So what we have introduced a couple of years ago was the so-called collision monitoring or collision event pipeline that then tries to bring an organization into the whole problem from pre-collision to post-collision, starting with detection, isolating the contact, monitoring the contact forces over time, and then classifying obviously and reacting to it is somewhat a low-level machine learning and planning problem. So these things we have been doing from the beginning. However, there's still a lot of work that needs to be done. But I think so far could be safe to say was roughly solved also commercially, and it has been introduced into all kinds of commercial applications on different robots. is detection, isolation, identification work we've been doing. And here you can see some of the basics. So instead of just, using the Lagrangian dynamics, we actually reformulate everything into momenta space, introduced what we call a momentum observer, essentially being a reduced order disturbance observer in nonlinear form. And then what you can show, if your models are quite accurate, then you can show that without the need of acceleration measurements, you end up with an estimator that essentially gets the external torques as a first order filtered version. So as nice as it gets, given that you have no acceleration measurements. So what you can get then is essentially very accurate contact measurements with this system. So here you can see one of the recent works we've been doing, where you can see that in this particular example, some static forces can be very nicely measured up to 1/10 of a Newton. The system is able to monitor them just with a method and some obvious extensions that need to take place over the years. However, the fundamental idea is roughly the same. Then 1/10 of a Newton can be added, giving you essentially a very accurate measurement of the forces. However, if you look at these methods, then typically what you get is some limitations, even though they work also on a very nice practical level. However, they typically have some noise, which gives you some thresholding and also some lagging in terms of, because it's a first order system, we obviously get some lags, so non-ideal behavior in terms of collision detection and monitoring. So we did put some work into trying to understand, can we, instead of use this classical observer-based methods, actually shoot for the direct method? And obviously we all know that we don't have acceleration measurements in the systems. So we asked ourselves, what can we do in order to get rid of this whole observation and lagging problem and thresholding? And obviously the solution sounds a bit naive. However, it was technically not that easy, is to get some accurate estimation of the velocity of the acceleration in the joints and also some velocity estimates, and then basically use the algebraic estimation of the external torques. However, obviously numerical differentiation has been a problem for many years, and this obviously increases the uncertainties in the residual R. So we need some large thresholding and filtering compared to what could be ideally possible, especially in high dynamic collisions. So what we came up with was essentially a new way of looking at the acceleration, and we essentially tried to make use of IMU measurements to get via nonlinear estimator and fusing with standard proprioceptive sensing to then estimate the velocity and the acceleration as accurate as possible. And the result was kind of, I think, quite interesting, that if you see here now a robot equipped with an IMU at the end effector, we see now during this collision, that is high speed measurement in the plate, we see the upper measurement here. You see just, I don't know, maybe 20 milliseconds or less of impacts. The momentum observer obviously has the lag because of the first order filtered version. If you do some offline processing and try to do some lag-free filtering and compare it, you can, if you want to just use position measurements, you cannot get accurate estimation because you have to filter so heavily. However, with this new method that essentially uses IMU measurement, fuses it with motor joint measurements and so on, you actually get an estimate of the collision that is quite accurate, not only in the dynamics, which you see here, the high filter frequency actually passed through. So we get up to maybe 50, 70 hertz of estimation, if not higher. And also the transient behavior is nicely captured. So in some sense, we think that we now found a solution that could get rid of all the limitations of standard algorithms that we've seen so far. However, obviously at the cost of adding some new sensing. Still some work needed to show that this really works in full robot, but the first results were quite promising. The fourth part I want to talk about quickly is obvious interaction control. So we all know the works like impedance control and admittance control. However, one of the main limitations, if we look at these works, is that despite we can basically, despite we can essentially be compliant without knowing the environment, which is obviously a very nice property of a robot. We can also do I think there's also sound. Sorry for that. We can obviously do force control also with these systems, regardless of the compliance of the environment, which obviously in interaction with humans is very important. Safe contact force estimation and also control. So not only being soft, but really accurately regulating the contact forces at the same time, which is, I think, very important in various applications, and obviously doing this also over many kind of various time frames. So we can see here up to 3 Hertz of accurate force control with internal measurements. However, one thing that we all encounter if we do force control or impedance control and we want to regulate forces, we kind of have inherent pre-storage of energy in the springs of the joints, or we have inherent undefined contact forces if we remove the contact, obviously in the force control test. So this is the two of the fundamental problems. So force control basically runs into the ground. Impedance control is a preloaded spring that then releases instantaneous energy and is highly unsafe. So what we've been doing over many years now is to fuse basically impedance and force control in order to get best of both worlds. However, both have significant limitations in terms of safety if you want to interact with the environment. So if you basically want to come up with a very naive control law, basically fusing impedance and force control together, then obviously you get both problems I was just showing you. So both of them would basically be unsafe in terms of contact loss, for example. So what we basically put together was starting with these naive force impedance control and then running through what we call a passivity analysis and contact stabilization test to essentially look at the so-called ports that can potentially destabilize force, respectively impedance controller in these hybrid setups where you don't only want to be compliant, but also very accurately regulate the forces. And we ended up with what we call the passivity-based Cartesian force impedance controller. This system essentially looks at the storage function of the system. So obviously this being the storage function of the tracking error. And what we can see there, if we look at its time evolution of the energy, so the power, we have 3 ports that potentially are unstable. And the nice thing is this port is not only there for rigid body robots, but also for compliant robots, for flexible joint robots. So this is basically a fundamental aspect looking at the feed-forward forces that we want to apply on the velocity, the desired velocity in the forces, and the desired velocity in the external forces. So these are 3 ports we need to take care in order to stabilize these systems. So essentially putting together a tank-based controller that then essentially looks at all these different ports. So as I said, 3 ports, where we then essentially monitor the energy and reduce it out of the system if we run into certain problems that we didn't come up with. So what we see here now is basically how these systems can deal with this problem. So we have accurate force control, and despite loss of contact, the system is able to regulate very accurately the contact forces without destabilizing or being unsafe. So this kind of energy regulation that I was now running through so quickly is very important to not only regulate forces accurately, but also deal with these unstable tasks that you see here. And what you can see in the upper plot is an accurate force controller. So the force error is basically below 2 Newton, despite the robot has no idea how the environment looks like, and this highly unstable zigzag that you see here. So what we have then been developing further is what we call the valve-based approach that then obviously tries to regulate the energies that you give the system depending on the task. And with this, you basically get a gain scheduler, not in terms of control gains, but in terms of energies in the task. And this is the last thing I want to talk about because I think otherwise I would be running out of time. So what we've been working on over the last 3-4 years, and we are really pushing this a lot, is now, can we actually have robots interacting with humans in multiple directions? So for example, moving in one direction with establishing a force control task, and the other one trying to establish a contact force, and then trying to regulate the energies in the system so that we can keep the task. So try to do it as optimal as possible, be safe, but at the same time, budget energies along the different valves, which we call that, and then have a gain scheduling approach that tries to essentially prioritize on energies and not so much on, as in classical control, in velocity, in kinematic control, multi-priority controllers, or in multi-stage controllers with various torque tasks, for example. So we try to essentially now budget energies instead of kinematic or force stages. And so far this seems to be quite nicely working because it's very easy to budget energies and learn energies also during iterative learning processes, which could also be a way to then fuse together with reinforcement learning, but that's a totally different story. And I think I just want to close with a last video that tries to lump things together, showing you how these systems can then be used for doing various tasks. And have some energy budgets, which you see here. So we essentially give robots an energy budget. So you could now connect batteries in some sense, and they would basically be able to plan their own battery status with this approach and make sure that they don't exceed the energy that was given to them. So this robot is now basically doing a filing task. Then, and in a way that, you know, despite the robot does not know how long he's filing, he will now basically detect the contact lost. And then, as you see here, starts now with the thing again. So this is now some low-level intelligence you get into the system. And on the other side, what you see here now is a robot that is doing a polishing task and also having the same capabilities, interaction, safety, but also dealing with control tasks based on energy budgets. And with this, be able to deal with all the uncertainties and all the different things that you cannot specify a priori in a task. So this is something you see here now on the left side. So the robot is now doing the polishing with the force controller, and then basically detecting that the end was reached, and then using this as a feedback to replan and to the things that we've been dealing with. Okay, that would be the last thing. I would like to thank obviously all the various supporters and collaborators, and I hope I still have at least a minute for some questions. Thanks a lot.
Thank you so much. It was a quite interesting talk. So sorry that we lost the first part of the.
Don't worry.
But now we have a few. Yeah, we have at least 2-3 minutes for a few questions, and we have one first question, and it is, how do you determine the value of the tank to ensure safety in human-robot interaction? These might depend on which human is in the vicinity and which body part, frail versus a sturdy human, for example. How can you modify the value of the tank at the runtime without generating again instabilities?
Yeah, okay, that's a very deep question, I guess. So in some sense, whoever asked the question caught me, because this is some prior knowledge I would assume to be given from, you know, all the great perception people, and who would, in some sense, this is, I guess, the prior information you need to be sure that this exists. So knowing the human who is on the other side, who is your interaction partner, knowing the right level of, or at least to some extent, have a conservative estimate. And in the end, if you don't know that, so if it's certainty based, you could always go with the most conservative one. So if you have at least some estimate of what would be the worst case that you could expect, you could always run and be as conservative as possible, meaning you would take the most fragile person, you would take the most conservative thresholding. However, obviously, because this is a trade-off, the more you know, the faster, the more high performance you can run. Obviously, the less you know and the higher the uncertainty, the more cautious you have to be. So, I mean, it's a little bit like driving a car. You can drive very fast if you know the road, if you have driven it 20 times. And if you have fog and it's a curvy road and you don't know exactly what's coming, you to some extent have to be very cautious. The other thing is, I guess, what is important is fundamentally energy can be nicely related to biomechanical impact. So I was talking about the mass and the velocity. So in some sense, this is a control and a design unified representation. Obviously, you have to understand how energy affects the human integrity in collisions, which is still some ongoing research, and many years will come before we can really go on this broad scale of the content of the workshop. But I guess the idea is scalable. That's what I wanted to kind of give. And however, without perception, obviously, or at least without indirect knowledge of knowing the right boundaries, it's always hard to, I mean, then in the end, you try to rely on the safest and most conservative control, which however you can do, right? I mean, it's not that it doesn't work. It's just that you have to sacrifice performance. Yeah.
Okay, thank you very much. We have one more question. What about closing the loop with vision?
On a philosophical scale or on a technical scale? Well, I mean, I think I tried to answer the question before. Actually, one part I skipped in my talk due to time was essentially trying to give you the first glance of how do we fuse this with vision. So obviously, there is the question of the worst case is the impact, but you can basically increase performance a lot if you have some notion of distances, some notion of what the first question was about, of who is it I'm dealing with. And this is exactly what we are also working on here. So I can just at least show you some. I think I saw Matej is also here. So together with Matej Hoffmann, who is also today in the audience, we just recently published a paper on essentially trying to show that some global and local behaviors can be put into local motion planning based on that are compatible with the safety analysis we're doing. So I don't want to go into details, but the idea is essentially that also global properties can be propagated back into how do you deal on the safety level. So how do you shape the right velocity that you want to drive at, and depending on the foreseeable action and the foreseeable future captured in some local properties, you might actually close the loop with vision exactly on that level. And the easiest one is obviously, or the most, the clearest one is to, that also relates to the first question, is given that I would have suitably accurate and reliable vision, I could then deduce which body parts are the closest ones, and then basically load the right data and assume the right data. However, there's still maybe some way to go, because at least in real world applications, there's some certification that you would have to go through, which I would argue is at least not to my understanding, a solved problem yet in technical terms, not so much in research terms, I guess.
Okay, thank you very much.
Yeah, hi Sami.
Hey, Oud.
I asked the first question. So imagine that you change suddenly that you have this body part, which is incredibly sensitive, very close to the robot, and you have to change your tank and you have to lower enormously the energy. Would that not generate instability, or would that simply not make it impossible to do certain tasks because then the force would be too low? And I know it's an open problem, but I don't know if you have any thought as to how to handle that.
Yeah. So that's actually the perfect question, exactly on the instability question. So this gain scheduling I was talking about in the last part is essentially, is essentially trying to address that. So the conservative strategy question, I guess, at least that would be my 2 cents on that. Depending on what you want to sacrifice. If you want to have safety, the absolute boundary, then obviously you would lose the performance. It wouldn't lead to instability because you lower energy. So you would basically, it's more like dissipation. So you would actually increase stability if you do it the right way, obviously. If you do a, let's say, non-dissipative character scheduler, then I guess this would be a problem. However, in the example you just gave, given that you would know you're close to the larynx, and you want to basically increase the safety, you would drain energy out of the tank or schedule energy out of the tank, which is essentially dissipation. It's instantaneous dissipation. It doesn't mean that that you like the behavior. That's maybe a bit the question you're raising. So the behavior is always so switching energies obviously means jumping. So you still need to schedule. So the valves are intentionally valves, which I showed you. Wait, just let me. I just open or make this a bit bigger. Oops, sorry. Does this work? Yep. Okay. Wait. Online PowerPoint. Okay, so this is exactly why we are working with gain schedules for the valves. So these valves are essentially not switching energy, but they are draining the power flow. With this, you ensure that you get continuity in the behavior. So you ensure stability by the framework, but you ensure continuity by these valves. So this is something I think we published 2 years ago, which essentially is the framework to then get the desired behavior you would like to, but it's a design question in the end, I guess. So that would be my rough approximate answer, however, not yet backed up with full experiments and the full understanding that this 100% solves what you were raising. But that would be my view on that.
Thanks. Thank you. Thank you very much.
Thanks for the question.
It was a quite interesting talk. We have more questions. I hope you can address them in the chat. And we will try to go into a short break,